Today we're going to talk about types of crystals and their properties. When atoms, molecules, ions go into the solid state, how can they be found? Well, we've talked about two types of crystal structure. It's our hot dog sheet. Let's do a quick review to remember that in ionic bonds we tend to have a metal to a nonmetal. Electrons are transferred. The energy involved in forming these crystals involve ionization energy, electron affinity, and lattice energy. Usually the electronegativity difference is quite high. When ionic bonds are formed and the electrons are transferred, we form cations and anions. We describe these compounds as with their empirical formulas or formula units. As far as properties go, they tend to have high melting points and high boiling points. They tend to be hard and brittle, and they cleave along a plane. Conductivity? Now that's going to change depending on the form. Because if you have conductivity, this is going to require two things: flow of charge. So in the solid phase, these ionic bonds are not going to be good conductors. There is no flow. In the liquid phase, however, that's fine. You have flow and you have those cations and anions. They are good conductors. If you were to take an ionic compound and dissolve it in water, it would be a good conductor. And I've talked to you about this by showing you a picture of NaCl. When it dissolves, going to form Na cations and chloride anions in solution. You know, these tend to be solids. Ionic compounds tend to be solids. And if you look at examples, good examples of this, you see that sodium chloride in its 1:1 ratio of sodium to chlorine, calcium bromide 1:2 ratio, magnesium sulfate. These tend to exist in ratios of small whole numbers. And remember our definition, or the way we think about conductivity. There must be flow of charge. Now compare this to covalent bonding. And when we look at covalent bonds, we have nonmetals to nonmetals. They share electrons. The energy involved in making these compounds is bond energy. There can be polar or nonpolar covalent bonds. Now, the cutoff points for electronegativity differences can vary depending on your book or your teacher. But for me, I like to use for my nonpolar cutoff an electronegativity difference of less than 0.4. And the reason for that is here, I'm always thinking of the C to H bond. As a biochemist, this is very important to me. So I think of that example of a nonpolar bond. Anything where the electronegativity difference is very close to 0. And then for a polar bond, something greater than 0.4, and I should put between 0.4 and 1.9, to me is going to be polar. Remember that these are going to form, big word, neutral molecules. This is going to be very important. They have molecular formulas, low melting points and boiling points. They are soft and easily deformed. Conductivity? That's not going to happen. I'm going to say no at this point, but we'll discuss it further. The reason I'm going to say no at this point is there is no charge. Examples, look at the phases that we have here. Solids, liquids, and gases. Carbon dioxide gas, water liquid. A glucose molecule is in the solid phase. It's a sugar. And I2, look at your periodic table. Iodine is a solid. Now, how does this get us into types of crystal structures? Let's take and reorganize our information like this. If we reorganize our information, we're going to talk about types of crystals and their properties. And what we have here is a comparison of the two types of crystals we've discussed. Ionic crystals could be things like sodium chloride, lithium fluoride, magnesium oxide, or calcium carbonate. They are going to be held together by very strong electrostatic forces of attraction. If you think about it and you look at the crystal lattice, or you look at the unit cells, the lattice points, at the lattice points, what you're going to have are your ions. And so these ions at the lattice points on the unit cell are going to give us strong electrostatic forces of attraction. And this explains our general properties of ionic bonds. They are hard, brittle, they cleave along a plane, they tend to have high melting points, and they are, as a solid, poor conductors of heat and electricity. We can now compare this to, now this is going to be a little different because I've talked about covalent bonding, and this is where they're going to nail you because even though these compounds are held together by covalent bonds, the truth is that in the crystal structure, these form molecules. Remember, covalent bonds form neutral molecules. So in describing the crystal structure, instead of saying covalent bonds, we say that it is a molecular crystal. You see the examples: argon, carbon dioxide, water in the liquid or in the solid, glucose, sugars, and iodine again. What holds these together? Well, weaker van der Waals forces of attraction. We've discussed these: London dispersion, dipole-dipole, hydrogen bonding, and depending on the substance you're looking at, you've got to evaluate what forces are present and to what extent. But if you compare these properties, remember that what's going to be at the lattice points in the unit cell will be atoms if you have something like argon, or molecules if you have something like carbon dioxide, water, sugars that you were talking about. These general properties are going to be that the crystals tend to be softer than those ionic crystals. They tend to have lower melting points, and they are poor conductors of heat and electricity, mainly because there is lack of charges present. Well, at this point now we have 4 types of crystals that we want to discuss. And all we've talked about is 2. We have a pretty good understanding of ionic and molecular crystals. So what we're going to talk about now is a new type of crystal. And this crystal is going to be described as a metallic crystal. Metallic crystal. We'll come back to this page in just a minute, but for now, let's talk about metallic crystals and their properties. You know, this is a pretty crude drawing, but let's take a look at what we have here. If I were going to think of metallic crystals, I would think of things like sodium or iron, copper wires, and even mercury. It's a liquid. Now, if we were to look at the crystal lattice and we wanted to look at the unit cell and what is going to be found at the lattice points, what we have are positive ions. Positive ions at the lattice sites. Now, I'm going to try to draw what I think of when I think of a metallic solid. Well, since I think of copper wires, let me draw my wire. And let me put, let's just make it a copper wire. And so what I'm going to draw here are going to be the kernels of a copper atom. And you know that this atom of copper generally is associated with having two loosely held valence electrons. So now what I'm going to do, and I don't really care if you see what I'm doing or not, is that I'm going to draw lots of copper atoms in the crystal lattice. And what you have is a situation where you start to wonder, to which kernel does this electron belong? To this one, any of the neighboring central portions of the atom. And so what we have here is a situation where the electrons, being loosely held, do not belong to one particular kernel. Instead, these electrons belong to the crystal as a whole. They belong to the entire crystal. The electrons belong to the entire crystal. All right. Now, another way of thinking about this is that these central parts of the atom, the kernels, are floating in a sea of electrons. Some textbooks refer to this as the kernels are surrounded by an electron gas. But the description is trying to get you to the same point of view, that these electrons are capable of movement, a sea of electrons, a gas of electrons. These have lots of motion to them. And so, what happens to this wire is, if you were to take it and stick it into an electrical outlet, and here comes electrical charges, and electricity we think of as being the flow of electrons. Here comes the electricity in this direction. And what are these electrons going to do? They're going to be repelled by the electrons coming in. The electrons are going to be moving in this direction. And so we have a lot of electron flow. What is a property of metallic crystals? They are very good conductors of electricity because there is flow of charge. So let's fill in our metallic crystal sheet here. Good examples of metallic crystals would be things like sodium, iron, and copper. And what would the forces be that holds them together? Well, these metallic crystals are held together by what's often called a metallic bond. A metallic bond. And if we have a metallic bond, these are non-directional covalent bonds that involve electrons that are delocalized throughout the entire crystal. Delocalized electrons. Now, these delocalized electrons help us understand the properties. The properties are going to be good conductors. Melting points, boiling points, all these other properties vary greatly. We'll talk about these in class. These vary a lot from one crystal to another. And what we have at the lattice points in these are going to be the kernels. I guess we would describe these as, let me see, how would I want to put this? Well, it's going to be, the kernels of the atoms. So I guess the positive ion. We'll continue this later.